Hi there, my name is Isaac. I'm the embedded tutor for Physics 212 this semester, and I just wanted to start a video series kind of walking through some of the crucial ideas of the course. So this is the first one, and we're looking at just Coulomb's law. We're going to look at the force between two charged particles and the electric field created by a charged particle at some location in space. So it's important that we start off with just two charges so that we kind of get a feel for Coulomb's force law, and then we can kind of break it down, and using some techniques that we'll discuss, we can solve really for any number of charges. One of the important things about this course at this point is that we're dealing with electrostatics, and so none of these charges are moving, which, if you could imagine in your head, you take this charge and you nail it to a board, and you take this charge and you nail it to a board, and then you see what kind of forces that one charge is applying on the other. And of course we know Newton's third law, so if Q1 is applying a certain force on Q2, then Q2 must apply an equal and opposite force on Q1. So Newton's third still applies here. I wanted to do an example with two charges, one with a negative, a Coulomb charge. So you remember Coulomb is the quantity of electrons. It's the unit of charge. And Q2 is going to be a positive charge. Now we know from growing up and learning things about charges is that like charges repel and dissimilar charges attract. So we've got two opposite charges here. So we know that Q2 is going to apply some force on Q1 that's going to be attractive. So this would be the force that 2 applies on 1. And due to Newton's third law, there's also going to be an equal and opposite force that's the force that 1 applies on 2. All right, so here's the equation in its original form. It's the force between the force of two charges enacted on each other is equal to the product of the two charges, so one charge times the other, divided by 4 pi epsilon naught r squared. And one thing that I think is really important to start with early on is there's two ways you can do this. You cannot draw the vectors out and put in the negative signs for charges and positive signs for charges, but this way is the way that I do it, and I've always preferred it. I draw my charges, I draw a diagram, which I really do like drawing a diagram, one of the more important things that I do in physics. And then I draw which direction I know the forces should go based on the charge orientation. Now, if you draw these vectors, before you do this equation, what I want you to do is drop the negative sign off everything. So really, if you pick which direction the vectors must be going, then you're actually going to be taking the magnitude of Q1 times Q2. So I just drop the negative sign when I do calculating because I've already drawn which direction it'll go. And you remember, force is a vector, so it adds like a vector. All right, so in this case we have Q1 is -1 microcoulomb, Q2 is 2 microcoulomb. Remember, I'm dropping the negative because I already picked the directions. Divide by 4 pi, epsilon sub naught's 8.85 times 10 to the minus 12. I can't quite remember the units for that. And then let's give them a distance. So their r is the distance apart they are. Let's say it's 2 meters. So 2 meters squared. And so at this point, you would just work out the math. And what you've been given now is you've been given the force that one applies on the other. And so this could be force 1, 2, or because of Newton's third law, force 2, 1. They have to be equal and opposite. All right, so this is one way to write it. And I would like to, actually let me point something out real quick. The electric force. Okay, So there's another way to write this, and that is to combine 4 pi and epsilon into a constant. So we're going to define a constant K electric, which is going to be defined as 1 over 4 pi epsilon sub naught. This is sometimes known as Coulomb's constant. So wherever there's a over 4 pi epsilon naught, we're just going to replace it with a K, E. So this is an easier way to write it, where Ke is something like 9 times 10 to the 9, but don't hold me to that. So some constant times Q1 times Q2 over R squared, the distance between the two. Now, one of the reasons why I love this original equation is because it's painting a picture for us. When you look at this one, you might wonder to yourself, why does force vary as 1 over R squared? How come if I half the distance, I how come if I half the distance, I quadruple the force? And so, we bring this half as close, and now I have 4 times greater field strength. Or not 4 times greater field strength, but a 4 times greater force between the two. So let's take a look at Ke. It's 1 over 4 pi epsilon sub naught. And you'll see here we have R squared. So let's focus in on this. Let's focus in on 1 over 4 pi R squared. So that is a term that's part of this force electric. And if you remember, 4 pi R squared is the equation to calculate the surface area of a sphere. So when you have a charged particle, in this case positive, we have these field lines that are emanating from it. And of course, this is just how we like to imagine it, so this is a model. And you'll notice that if you, like, for example, drop a rock in a pond, you end up with a circularly propagating wave. So, in other words, at some time, there will be a sphere around your charge where that electric wave is at now. I guess it's a field in this case. And you'll notice that as you draw the ring further and further out, the amount of lines to circumference here is much less. Now this is a 2D image, so imagine this is 3D. So you'll notice that as we draw our circle or our sphere bigger and bigger, the density of electric lines decreases. And that's because you can't have electric lines starting anywhere but at a charge. And so at the charge, there's a fixed number of these field lines, and as we go about it in a circle from the center, with the charged particle at the center, we end up with a sphere. And the amount of lines, in this case, we're going to go ahead and say that the amount of lines is going to be equal to Q1 times Q2 divided by epsilon sub naught, the permittivity of free space. Okay, so this is going to be the amount of lines. This is the amount of lines, and we're interested in what the amount of lines density is with the surface area. So the density of a given number of lines, if we want to know the density at some point on the sphere of some radius, then we have to take the number of fixed lines that we know we started with and still have, and divide that by the surface area of which they're spread out. And remember, the surface area of a sphere is 4 pi r squared. And so you'll notice we can work this out, and we end up just getting the equation as we first wrote it. So we end up with Q1 times Q2 divided by 4 pi r squared epsilon sub naught. And we're back to where we started. So I just think that's really clever and kind of cool, the fact that the reason why why the force of the electric field decreases as 1 over r squared as we go further and further away is because everything in this universe tends to propagate in a circle. And so if we were living in flatland, then, now imagine we just have a flat thing, we have some given number of lines. But now we don't have a third dimension, so we're going to look at the density of the lines around the perimeter. Well, the perimeter, the circumference, is 2 pi r. So in a flat world, in a two-dimensional world, the electric force would vary as 1 over r. But because we're in a three-dimensional universe, it varies as 1 over r squared. So I went a little longer on that than I intended to. Hopefully that kind of gives you a good visualization of why the equation looks like it does. So anyways, I'll see you next video where I'm going to continue with kind of this same line of reasoning. So yeah, hope this was helpful, and see you next video.